Welcome to this explainer. Today, we are diving into a world where absolute microscopic violence creates perfect macroscopic precision. When you look at the incredibly smooth surface of a smartphone screen, the flawless mirror finish of a telescope lens, or the high-performance bearings humming inside a jet engine, you're actually looking at the results of a process that is, at its core, incredibly chaotic. We are talking about the hidden world of precision grinding.
All right, let's kick things off by defining our main tool here. And honestly, this might just completely shatter how you think about sanding or grinding. We typically think of grinding as rubbing two things together to wear one of them down, right? But in the world of high-precision manufacturing, an abrasive is formally defined as a very small, hard particle having sharp edges and an irregular shape. So it's not just friction, it's a highly calculated attack on a surface. Just look at the jagged, almost alien landscape of this single grain of aluminum oxide under an electron microscope. See those aggressive angles? When this microscopic rock is dragged across a piece of metal, it proves that grinding isn't just rubbing at all. It is actually a microscopic cutting process. Every single tiny point you're looking at acts like an individual blade on a microscopic saw.
To really wrap our heads around this, we're going to jump scales today. We'll start with the microscopic cutting edge, then look at the anatomy of a wheel, dive into the physics of grinding, and finally explore the machines of precision.
Section 1. The microscopic cutting edge. Let's start incredibly small, right down at the micrometer level, with the abrasive grain itself.
You can clearly see the blocky, totally irregular shapes of these grains. Whether we're looking at aluminum oxide or diamond, these shapes are entirely random. And what that means is, when they strike a metal workpiece, they hit it with massive negative rake angles. To put that simply, imagine trying to peel a carrot by pushing your knife backwards, almost flat against the surface. It takes a massive amount of energy to scrape metal away like this, but these millions of tiny cutting tools are hard enough to actually pull it off.
We generally split these tiny cutting tools into two main camps. First up, we've got conventional abrasives like aluminum oxide and silicon carbide, which are used for your everyday metals and alloys. Then we have the super abrasives, cubic boron nitride and diamond. These are literally the hardest materials known to humanity, reserved for highly specialized jobs. But here's a totally surprising fact. You actually cannot use diamond to grind standard steel. Why? Because at the extreme temperatures of grinding, the carbon in the diamond physically dissolves chemically into the iron of the steel. So matching the exact right microscopic tool to the right material is an absolute science.
Now, this brings us to an absolutely crucial concept called friability, and it introduces this wild engineering paradox into how we design these grains. Friability is the ability of an abrasive grain to fracture into smaller pieces under stress.
So why on earth would we intentionally design our industrial cutting tools to break? Sounds counterintuitive, right? Well, think about what happens when an abrasive grain scrapes against hard metal thousands of times a second. It gets dull. And if it stays dull, it just creates immense heat and friction, basically burning the part. But by engineering the grain to be highly friable, it shatters under pressure exactly when it gets dull. It's just like snapping a dull piece of chalk in half to expose a brand new sharp edge. It allows the whole grinding wheel to continuously self-sharpen.
Section 2. Anatomy of a wheel. Let's zoom out a bit and see how we assemble millions of these individual self-sharpening grains into a single cohesive tool.
When you really zoom in on the surface of a grinding wheel, you realize it isn't just a solid chunk of rock. It's this beautifully engineered matrix of three distinct things. First, you have the sharp abrasive grains themselves. Second, the bonding material, acting like tiny supporting posts holding those grains in place. And third, and this is wildly important, empty space. We call this crucial empty space porosity. If you don't have enough empty space in the wheel, the tiny shavings of metal have literally nowhere to go, they clog up the wheel, and the whole cutting process just grinds to a devastating halt.
The real secret sauce of a wheel's performance often lies in that middle element, the bond. The specific strength of the bond determines the wheel's grade and toughness. You've got vitrified bonds, which are essentially glass and ceramics fired in a kiln at a blistering 1250 degrees Celsius. They are incredibly rigid. Then you have resinoid bonds, made of thermosetting plastics for a bit more flex. There are even flexible rubber matrices for specialty blades, and solid metal bonds used specifically to hold on to ultra-expensive super abrasives like diamond.
All of this careful engineering, the grain, the bond, the porosity, it all scales up into the perfectly balanced, highly structured wheels ready for heavy industrial use. We're talking everything from wheels just an inch wide to massive drums several feet across, all engineered with the exact same microscopic precision hidden on the inside.
Section 3. The physics of grinding. Let's look at the sheer violence of the physics involved when the wheel finally meets the metal. Okay, this is a massive realization. Grinding is actually removing tiny, long chips of metal. It's exactly like a macroscopic lathe or a milling machine. It's just happening with millions of randomized cutting teeth all at once.
And for absolute proof of that, check out these electron microscope scans. In one image, you can literally see the coiled metal swarf. Those are the microscopic chips shaved right off the surface of the workpiece. And in the other, that perfect tiny sphere is a melted metal globule. It formed because the heat of the scraping was so intense that the chip liquefied and surface tension pulled it into a microscopic ball right before it cooled down. Which brings us to this mind-blowing fact. You know those iconic, beautiful orange sparks you see flying off a piece of metal when someone uses a grinder? Yeah, they aren't pieces of the grinding wheel. Those sparks are actually the microscopic metal chips reacting with atmospheric oxygen in an intense exothermic reaction. The peak temperatures where the wheel meets the metal can reach a staggering 1,600 degrees Celsius. Without constant flows of cooling fluids, that kind of heat could fundamentally alter the metallurgy of the part and completely ruin its strength.
Now, surviving that extreme environment means the wheel goes through a very specific life cycle of wear. First, it wears down through attritious wear, which is just the grain dulling over time, essentially acting like a pencil losing its sharp point. Then, as we talked about, grain fracture kicks in to reveal new edges. Finally, bond fracture happens. Those little posts holding the grain actually snap. This releases the completely spent grain, letting the wheel shed its old skin to expose a totally fresh layer of sharp abrasives underneath.
But here is where things get really tricky. A grinding wheel is not a static tool. A specific wheel's performance changes dynamically based entirely on the forces applied. If a wheel spins faster, it acts harder. If the workpiece spins faster, the wheel acts softer. It's a delicate balance requiring constant monitoring. And when a wheel gets too dull or loaded up with metal, the machine has to run a conditioning process called dressing. This uses a diamond tool to physically crush and cut the outer layer of the grinding wheel right off, completely restoring its perfect shape and sharpness so it can get back to work. Section 4. The machines of precision. Finally, let's zoom all the way out from the micrometer to the massive machines that actually wield these abrasive wheels in the real world. To hit dimensional tolerances smaller than a single micrometer, modern manufacturing relies on incredibly rigid, computer-controlled machines. You've got surface grinders holding flat parts tight on magnetic chucks, cylindrical grinders rotating round parts, like engine crankshafts, and internal grinders spinning tiny wheels inside holes at upwards of 30,000 revolutions per minute just to make absolutely perfect bearings. These massive machines pull off an incredible mechanical dance. The workpiece is locked down with absolute rigidity. The wheel accelerates to speeds up to 150 meters per second. Guys, that is over 330 miles per hour. As the wheel gently touches the part, sensors are monitoring the acoustic emissions and power draw. Automatic dressers sweep in to maintain the wheel's profile, syncing the rotation of the part and that blazing fast wheel to gently shave off material at the microscopic level until submicron accuracy is finally reached. The ultimate result of all this controlled microscopic violence? Macroscopic perfection. It's an invisible precision. The gears in your car's transmission that shift silently, the artificial titanium hip joint moving without friction, the ultra-flat silicone wafers inside the processor powering the very device you're using to watch this right now. Absolutely none of our modern technology exists without the abrasive grinding process smoothing the way. We've explored the fascinating interplay of grains, physics, and machinery that keep our world running. But as technology relentlessly demands tighter tolerances, pushing us down to the nanoscale and eventually the atomic level, I'll leave you with this. What entirely new, unknown microscopic supermaterials are we going to need to invent to grind the technologies of tomorrow? Thanks for joining me on this explainer, and as always, keep your curiosity sharp.